Welcome to the Explainer. Today, we're going to unwrap something that seems pretty simple on the surface, but it's actually the key to how 7th graders learn to see the world in 3D.
I mean, you've been there, right? Staring at a gift, wondering how much wrapping paper do I actually need? Well, the answer to that question, it takes us straight into a core geometry concept that students are tackling every single day. All right, so to solve this whole wrapping paper dilemma, we've got to get our heads around one key idea in math: surface area. So, what is surface area really? The easiest way to think about it is this: it's the total space covering the outside of an object. Like if you were going to paint the whole thing, every single side. And hey, don't get it mixed up with volume. That's the space inside the object. Totally different things. And that's the big puzzle for students. How do you actually measure all that outside space on a 3D shape? It's a surprisingly big jump, right? Going from figuring out the area of a flat square to calculating the entire surface of a 3D box.
So, how did teachers help them make that jump? Well, the solution is actually really clever, and it all starts with one simple but super powerful idea. What if you just unfold the shape?
And that brings us to the real hero of our story today, something called a net. A net is just that. It's the flat, 2D pattern you get when you unfold a 3D shape. Seriously, just picture a cardboard box that you've cut open and laid out totally flat. That's a net.
And look at this. This is the magic of the net in action. You take a 3D shape, like this prism here, and you unfold it into this simple, flat pattern. All of a sudden, a really tricky 3D problem becomes a much easier 2D problem. You're not worrying about depth and angles anymore. You're just looking at a bunch of flat shapes that you already know how to measure. And once you have the net, the rest is, well, pretty straightforward. You just figure out the area of each one of those individual rectangles. And then you just add them all together. Boom. That final number, that's your total surface area. Simple as that. Okay, so we've got the basic idea of nets down. Now let's see how this whole concept applies when the shapes get a little more interesting, like when we start talking about prisms and pyramids. So in class, students learn how to spot the difference between these two. And it really comes down to a couple of key things. A prism, that's always going to have two identical bases, C, and its sides are rectangles. A pyramid, though, is different. It's got just one base, and its sides are triangles that all come together at a single point at the top. And when you see their nets laid out side by side like this, it just becomes crystal clear, doesn't it? Look at the prism's net on the left. It's mostly rectangles with those two square bases. Now look at the pyramid's net on the right. It's got its square base, sure, but the sides are all triangles. And pyramids introduce a cool new piece of vocabulary: slant height. Now listen up, because this is important. This is not the pyramid's actual height, from the very top down to the middle of the base. Nope, it's the height of one of those slanted triangular faces, and you absolutely need that measurement to figure out the area of those triangles. Okay, so this is all great, but why does any of it matter, right? Well, this is the part where the math jumps right out of the textbook and into the real world. Teachers will give students a problem that sounds something like this. Imagine you're a company that makes candles in all these different cool shapes. Well, if you can calculate the surface area, you can figure out exactly how much wax or material you need for the molds. Suddenly, this geometry lesson is directly tied to real-world stuff like production costs and pricing. And this is how you know it's for real. This is an actual question from a standardized test. The whole point is to see if students can take this kind of abstract idea of a net and actually use it to solve a concrete problem. It's all about moving from theory to practice. All right, now for my favorite part, the part I find absolutely fascinating. Let's pull back the curtain a little and see the how. How do teachers actually guide a student from being totally confused to that aha moment of clarity?
Well, if you look at the teaching guides, you see this really powerful strategy. Instead of just telling students the facts, teachers ask these very specific questions. They're called discourse questions. The goal isn't just to get the right answer fast. It's to start a conversation, to get the kids thinking and talking, so they discover the logic for themselves. That's how you build a much deeper understanding that actually sticks.
And the teacher's playbook is just packed with these awesome hands-on strategies. Things like using colored pencils to shade the different faces so you can see them clearly. Or my favorite, giving students big paper nets to literally cut out and fold up themselves. And this isn't just busy work, It's about building a physical connection to the idea. It helps students truly feel how a flat 2D plan transforms into a 3D object. So you can imagine, when they get a really complex problem, a really tricky shape, students aren't just left on their own to sink or swim. The teachers have all these tools ready to help them break it down.
Just look at this. It's an organizational chart, a template that teachers give out. It's basically a roadmap. Okay, first column, what shape is this face? Got it. Second column, how many of these identical faces are there? Okay, 2. Third column, what's the area of just one of them? And then the last column, what's the total area for all of those identical faces? It guides them step by step all the way to the final answer.
And what this shows so brilliantly is that the real goal here isn't just getting the right number at the end. It's about teaching a process, a structured, repeatable way to take a big, scary, complex problem and break it down into small, simple, solvable pieces. And let me tell you, that is a skill that they will use for the rest of their lives, way beyond this math classroom. So when you look at it this way, you realize that behind every single math concept, there's this really carefully designed journey of discovery. It's not about rote memorization of formulas. It's about building genuine understanding one unfolded shape at a time. And that just leaves me with this one big question. If we really understand how our brains learn, how does that change what we think education should be?